All right, so today I'm making this lecture on continuing our discussion about fluids in physics. Last time we worked on Archimedes' principle, which was all about buoyant force, floating versus sinking, things like this. Now we're doing hydraulics. And so hydraulics is an interesting topic, especially when it comes to engineering and things like this. It's a way of using some of the phenomena of fluid dynamics and statics and things like this to get some kind of a mechanical advantage, to make some machines, to help us do some work a little bit more efficiently than normal. And so I'd like to show how that kind of works. So basically what we're going to start with is, let's assume we have some system of cylinders. So let's say we have a nice big cylinder here, and it's going to be connected to another cylinder over here, which maybe is a little bit smaller. And these two cylinders are connected. There's a big continuous pipe there. Sometimes it's called a line. And inside of this cylinder system, we have a fluid. Okay, so there's some fluid which is inside of here. Now, one thing we remember when we started talking about fluids was that there's this pressure-depth relationship between how much pressure an object would feel while being submerged in a fluid versus how deep inside of the fluid it is. And we know the pressure is given by rho times G times H. So the deeper you are, the more pressure you're going to feel. Well, another thing to note is that the pressure at any depth, at a particular depth, I should say, in a continuous system like this, so there's not like little hatches or gates or something between here. It's this big continuous system. The fluid is flowing through perfectly normally. Then at any height you choose, so let's say at this depth right here, anywhere in this system at that depth, all of these places are all at the same depth. They all feel the same pressure, some P. Let's call it P1. And if we choose a different depth, let's say the surface, at the surface, there's some other pressure, P2. But everywhere at that depth, it all feels the same pressure. It turns out that if you're at the surface, then the pressure you feel is, of course, atmospheric pressure, P atmosphere. Because it's in equilibrium with the atmosphere itself. The atmosphere is pushing down on the fluid, and the fluid is pushing back up. And so they have the same pressure. But the deeper you go, the more pressure you feel. Okay, so now let's say we close off this system by using some pistons. So we're going to put a piston in here, right here. And let's say this piston we're allowed to push or pull. So we could push the piston down or pull it up, however we want. And there's also a piston over here the same way. Okay, so what's going to happen? Let's say we push down on this piston, piston 2. In fact, let me go ahead and erase this stuff right here. Let's say I have piston 1 is this guy over here, and this guy I'll call piston 2. The names don't matter. I just want to name these things so you'll understand. Am I talking about the big side or the small side? I'll call the small side piston 1 and the big side piston 2 for this particular example. Now, if I were to push down on this piston, then what's going to happen? Remember, all of this is filled with fluid. There's all a bunch of water or some kind of a fluid inside of here. Well, let's assume that the fluid we're talking about, I'm going to go ahead and call it water, but it could be some other fluid. Let's say this water is incompressible, which means you can't squeeze the water. You can't take a certain amount of water. Let's say you have a box of water. You can't squeeze the box and crush the box and make all the water fill a smaller space. It fills the space it does, and it cannot fill any less space. It's incompressible. Of course, in the real world, while water is usually called incompressible, and for the most part it is, it's not perfectly incompressible, but for our purposes, let's just say it's completely incompressible. Well, if that's true, as I push this piston down, well, what has to happen? As I push this piston down, this water that's here has to move out the way. So it gets pushed down. That pushes the water this way through the system, pushes the water up here, and that water then pushes on this piston on this side, because it has to get out the way. You're pushing down on the piston, you're moving the water. Well, obviously the other side has to make room because the water cannot be compressed. So what will happen is this piston, piston 2, will be raised a certain amount to make room for that amount of water you push down. Okay? Now here's the thing. If I push, let's say I push on piston 1 with some force F1. Is it true to say that that force you're pushing down, that force gets pushed into the water then pushes on piston 2, does piston 2 feel the same force that you pushed piston 1 with? Well, let's investigate. Maybe it does, maybe it doesn't. If it does, then this is kind of a boring lecture. Who gives a crap? But if I want some mechanical advantage, then it must be true, for it to be interesting, that maybe there's some difference in the force. Maybe if I push with a certain force, I get some other force out. And hopefully, that other force is actually more. Because then I could build machines that allow me to lift really heavy objects with really light forces. So let's see. If I push on piston 1 with some force F1, what do I know? Well, I know by what's called Pascal's law, the pressure must be the same, especially at the same heights. So or same depths, if I'm pushing on piston 1 with a certain force, that gives rise to a certain pressure, right? This piston is pushing on the water, a certain amount of force is pushing down, the piston has a certain size, and so that's going to apply a certain pressure, P1, to piston 1, to the water. And as I keep applying this pressure, that pressure flows through the water to the other side, and that pressure is going to try to lift up on piston 2. So piston 2 will feel some pressure, P2. Now the question is, if the pressure from P1 is the same as the pressure felt by P2, does that mean the forces are the same on both pistons? Well, let's look at what pressure is. Pressure, if you remember its definition, is force over area. Okay? Well, if pressure 1, which is force 1 over area 1, is the same as pressure 2, which is force 2 over area 2, then the force felt by by piston 1 over the area of that piston must be the same as the force felt at piston 2 divided by the area of that piston. But I know that piston 2 is much bigger than piston 1 in my example, and thus the area of piston 2 is bigger than piston 1. But if this number is different than this number, for these two quantities to be the same, this number has to be different than that number. So, what do we know? Force felt by piston 2, if I rearrange this algebraically, I move A2 up here, I get is whatever the force that you pushed on piston 1 with times the ratio of the area of piston 2 to the area of piston 1. Okay? So all I did was I said the pressure at piston 1 must be the same as the pressure at piston 2. I then wrote what pressure is by definition, and then I rearranged it algebraically for how much force piston 2 is going to feel. And I get this result. Now what this result tells me is if the two pistons are the same size, then A2 is equal to A1, and A2 divided by A1 then is just 1, and so the force at piston 2 is the same as the force at piston 1. Okay, boring result. However, let's say instead piston 2 is larger than piston 1. A2 is greater than piston 1. If that's true, A2 divided by A1 is a big number over a small number, which is a big number. A number bigger than 1, let's say. And if I have a number bigger than 1 multiplied by the force F1, then that means force F2 is bigger than force F1. And so that would imply that if I push with some amount of force, let's say 100 newtons on this small piston, then I'm going to get out a force of maybe 500 or 1,000 newtons from piston 2. Let's look at an example to see this in action. Let's get the actual numbers. Let's say we have the same kind of a system. Here's piston 2, here's piston 1, connected like this. Let's say R1, the radius of cylinder 2 is maybe 10 centimeters. And R2, the radius of piston 2, I'll give it as 50 centimeters. Okay, so there's our system. Again, I'm going to have some piston in here and some piston in here that I'm allowed to push or pull on. And there's a bunch of water in here. Now here's the question. If I push with a force F1 of, let's give it 100 newtons on piston 1, what is the force F2 at piston 2? How much force do I get out of this system? Okay, well, to solve this kind of a problem, we say the pressure at piston 2 is equal to the pressure at piston 1. And what do we know about pressure? That's F over A. So the force at 2 over the area of 2 is the force at 1 over the area of 1. I'm looking for F2, so I solve this equation for F2, and I get F2 is F1 times A2 over A1. Plugging some numbers in, I know force F1 is 100. What are these areas? Well, I'm going to assume these are cylindrical cavities here, and a cylindrical piston. And so the area of the piston is the area of a circular piston, and the area of a circle is just pi r squared. So this is going to be pi times the radius of piston 2, which is 50 centimeters. Centimeters is bad unit, so I got to convert to meters. That's 0.5 meters. And remember, it's pi r squared. Divided by the area of piston 1, again, pi r squared, pi times 0.1 squared. The pi's will cancel out here. And we get 0.5 squared over 0.1 squared, which is 25. So it's 100 times 25, or 2,500 newtons. So, what does this tell me? This tells me if I look at the small piston, I push on it with 100 newtons, then the big piston will lift up with a force of 2,500 newtons. 25 times as much force. And so this is very nice. This means I could design machines, like let's say I own a mechanic's garage and I need to get under the cars. Well, obviously, I'm not going to lift the car by hand, and maybe I don't want to use a jack or something like that. I could design some kind of a hydraulic mechanism such that I could push on a small piston with some small force, 100 newtons, 500 newtons, whatever, and design this system in such a way that this will lift up a much, much heavier object than my 100 Newton force could possibly lift. In this case, with only 100 newtons, I'd be able to lift 2,500 Newton weight object. Very, very cool. Now, if you go the other way, if you were to start at the big piston and you push with a force of 100, that's going to lift up on the small piston, but this time you're going to lose force. So, because this is a mathematical equation, left side equals right side, this same answer would tell me that if I push down at F2, at piston 2, with a force of 2,500 newtons, then piston 1 will lift with only 100 newtons. So you're losing force going the other way. So the first thing, obviously, is if you're going to design a hydraulic mechanism and you're trying to lift heavy objects, you want the big piston to be where the heavy object is and the small piston to be where you're pushing, because you're going to get mechanical advantage out of it that way. Going the other way, you lose force. Now, hopefully you believe this is true. I just showed mathematically it's true, and the principles involved are fairly basic. You were just saying the pressure flow in this continuous bit of a fluid is constant. So if you apply a pressure to one side, that same pressure goes to the other side. And because pressure is force over area, if you have a difference in areas, then you're going to have a difference in forces. Okay? However, it should be kind of worrisome if you think about it, because you're like, well, wait a second. I have things like conservation of energy and things like this. Surely it can't be this easy, that I can't just get free force from nothing, because I could just build an infinite machine that lets me use really small forces to lift very, very large objects, and maybe I could use it for something like this. Let's say we remember we have a hill, and you have an object up at the top of the hill at some height h. It's got some potential energy. As it slides down, it gains speed, and now it's got a bunch of kinetic energy. So it started with a bunch of potential, gains a bunch of kinetic at the end, and we know that if I then continue this hill and I try to make it go up higher, it can't. The highest this thing can get is the same height because of conservation of energy. However, what I could do is use some kind of a system like this hydraulic system to then use a small amount of force to take this box that was way down here and lift it to the top of this hill now, and then let it slide down again, and now it's going to gain even more energy. So I started with a certain amount of energy. Surely it can't get to this higher place, but I could use a little bit of energy to lift it a greater distance, because I could use a small force to lift something very heavy, something like this. Well, surely that can't be the real world, because if this were true, then we'd have infinite energy in the universe and we wouldn't have to worry about paying our bills anymore. So what is the balancing point? What is the thing which stops us from taking too much advantage of the situation? And it goes like this. We weren't very careful in this kind of presumption here about using energy and conservation of energy, because we're kind of conflating two different things. We're talking about using a small force to lift a heavy object. Those are force things. Versus here, we're talking about energy. Energy is what's conserved, not force. So, how can I not violate conservation of energy but still allow this kind of mechanical advantage to happen? And the way it works is this. With conservation of energy, remember, we have kinetic energy and potential energy and work. And the initial amount of energy is equal to the final amount of energy. Okay? That's what's true, the total energy of the system. And the energy is a combination of kinetic and potential, and then any work done on or by the system. Friction slowing me down takes energy away. A rocket pack on my back gives me a boost, gives me energy. And so this term right here, the work, is where the force is coming into play. Remember, work is force times distance. So what must be true is not that the force has to balance on either side, but the work has to balance on either side. Well, if that's true, let's look back at what's going on over here. Yes, by applying a small force to the right side, I get a large force on the left, but what would have to be true for everything to work out is not that the force is balanced, the work balances. So for the work to balance, I have to say that work 1 must be the same as work 2. But work is just force times distance, so it's F1 times x1 must be F2 times x2. So if F1 is small and F2 is big, in order for these equations to be true, x1 would have to be big and x2 would have to be small to balance. But does that make sense with our particular example here? Is it true that if I push down on piston 1 with 100 newtons and get 2,500 newtons out of piston 2, that in order to do it, I have to push a very long distance on at piston 1, and piston 2 only goes up a very small distance? Well, think about it. Remember, in this hydraulic system is a bunch of fluid, a bunch of water. As I push on F1, I'm moving the water out of the way, and that water moves over to piston 2's side, and that water is pushing up on piston 2. Well, if piston 1 moves from this height down to this height, notice all of this water in here is what was moved out the way. And so that water then is going to lift up piston 2 on this side and go over here. So now all that green water that was on the right is now over here on the left. But how much water is there? It's the volume of the water. This volume V1 is the area of the cylinder, A1, times, let's say, the height, Y1. So if my piston goes from there to there, I'm pushing down with a distance Y1. That's the volume of the water. It's the area of the cylinder times how deep I push. On the left side, we have the same thing. This V2 is the area of 2's piston times how high piston 2 is pushed upwards. And so just like the works being equal, another way of saying it, or a reason that this is true, is that actually the volume of water moved from one's side is the same as the volume of water moved on 2's side. So, volume 1, what is that? That's A1 times Y1 equals volume 2, which is A2 times Y2. So, another question I can ask is, well, if Y1, for our particular example, let's say I push down on piston 1 and I push it 5 meters downwards. The question is, how high, Y2, does piston 2 get lifted? Well, to answer that, I solve for Y2. Y2 is equal to Y1 times A1 over A2. Y1, I'm told, is 5 meters. A1, remember, that's pi times 0.1 squared over pi times 0.5 squared. The pi's cancel again. And now I get 5 over 25, or 1/5 of a meter. 1/5 of a meter, or 0.2 meters, 20 centimeters, means I was moving up 5. I was pushing down on piston 1 5 meters, and it only lifted up piston 2 by 20 centimeters, a very small distance. And that's my balancing act. With hydraulics, nothing's perfect. You get some aspect of mechanical advantage in the force, but you lose some aspect of mechanical advantage in the distance that these pistons are moving. So yes, I can lift up a really heavy car using a hydraulic jack or something, using a very small amount of force. However, in order to move it any appreciable distance, I have to push down on my piston a really, really long ways. In fact, the more mechanical advantage I get, that is, the heavier the object I'm trying to push up, the more I have to push in distance. And in fact, that gives rise to our two big equations for hydraulics. The first one, pressure at piston 1 is the same as the pressure at piston 2. And of course, the actual useful bit of this equation says that the force at piston 1 over its area is equal to force at piston 2 over its area. That's the first big equation. This lets us figure out how much excess force we get. Or I want to lift this 1,000 Newton object. Given my hydraulic system, how hard do I have to push at piston 1 or piston 2, whichever. The other equation is that the volume of water pushed by piston 1 must be the same as the volume of water pushed by piston 2. And of course, the useful bit of this equation says that the area of piston 1 times how far you have to move it is equal to the area of piston 2 times how far he's going to move. So, you want to lift a heavy object, you use a hydraulic system, you push on the small piston, and that's going to lift the big piston with a bigger force. However, in doing so, you're only going to move that big piston a very small amount relative to how much you push. Okay? So that's the balance. Maybe you want to go the other way. Maybe you want to move something a very large distance, but you don't have that much room to do it. Okay, well, use the hydraulic system in reverse. Start with the big piston, and you're going to try to move this small piston a very big distance. Well, in order to do it, you have to push really, really hard with a large force, but maybe you only have to move that big piston a meter, and that's going to move the small piston 50 meters, but you don't get as much force out of it. So, depending on what it is you're trying to accomplish with your machine, are you trying to lift something that's too heavy, or you're trying to move something further than your space allocates? If you want to lift something heavy, push on the small piston. If you want to move something very far, push on the big piston. But these are your two big equations, and with these, you get to calculate any of the kind of problems we're going to have in this class. Anyway, hope this helps, and I'll see you next time.